In this lesson we're going to look at the particle model for temperature, and we're going to see how the temperature of a substance is related to the kinetic energy of the particles that constitute that substance. Before we do that, let's just remind ourselves of how the particles in the solid, liquid and gas behave. So in this particular case we're really interested in how they move. So in the solid we have particles which are vibrating around a fixed position. They're closely held together and they're bound by quite strong forces. Now in a liquid the particles are still fairly closely held together, so they experience weaker cohesive forces between them, but those forces aren't strong enough to hold them in a fixed position, so they are free to move where they want, to change position. So this red particle here can basically go where it wants. It's free to move in any direction randomly within the construct of the liquid. Now the particles in a gas are effectively separated by much larger distances. We're going to call this gas an ideal gas, and in this ideal gas what we can say is that at any one moment in time the particles in the gas just possess only kinetic energy. So we can assume that there are no cohesive forces acting between the particles. Now that is not true for a solid and a liquid. Now because the particles in the solid and liquid are close together, they experience much greater cohesive forces, and because of that we can say that these particles not only possess kinetic energy, but they also possess elastic potential energy. So we can treat, for example, our solid as being particles which are vibrating around on springs. So you can imagine there are springs in between each of these particles. So as they're vibrating at any one moment, each particle will have kinetic energy, but will also possess elastic potential energy due to the springs that are holding it together. Now I don't want to go too far down this line. What is important here is we understand that the temperature of a substance or an object is directly proportional to the kinetic energy of the particles that constitute that substance, whether it's a solid, liquid or a gas. So we can say there, let's just fill in this statement. So the temperature of a substance is directly proportional to the average kinetic energy of its particles. So if I add energy to either of these solid, liquid or gases, for example simply by heating them up or adding heat, okay, what will happen is I will increase the average kinetic energy of the particles in each, and that will result in an increase in temperature. Now I would like to mention something very important here before we move on, and it is this, that although in each case the temperature of the solid or of the liquid or of the gas is directly proportional to the average kinetic energy of the particles, when I heat the solid or the liquid, it is not true that all of this energy is converted into kinetic energy. Okay, so some of the heat will be transferred into the elastic potential energy due to the cohesive forces that are holding the particles together. So not all of that heat is transferred into kinetic energy. Likewise, not all of the heat will be transferred into kinetic energy in the liquid. Some of it gets stored in the form of elastic potential energy due to the forces acting between the particles, the cohesive forces. Okay, it is only true and only true that all of the heat is converted into kinetic energy in the case of an ideal gas. Now you will see the importance of this idea when we come to talk about specific heat capacity in a later unit. Okay, so when we heat the gas, all of this heat is directly converted into kinetic energy in the particles. Okay, but not so in the case of the liquid or in the solid. Just emphasizing again that that does not affect this rule here, that the temperature of a substance, whether it's a solid or a liquid or a gas, is always directly proportional to the average kinetic energy of the particles that constitute that substance.